Engineering 305, Chapter 2, Problem 61. This is my last one for the night. Yay! Of course, I have a lot more to do, but the stresses on the horizontal and vertical planes at a point on the outside surface of a solid circular shaft subjected to an axial load P and a torque T. Don't let the extraneous information get you upset. What they're telling you is we've got this stress point, this little stress square, and it looks like that. And we know a couple things about it, and then we want to find the new stresses on this new plane. This is the same problem we've done every time, but you got to do something unique. You got to do something creative and new. Yeah, I messed up the camera. Sorry. So let's draw our little shape here. So I got my stress cube going on. My stress in the x direction is 8,000 psi. I've got stress in the y direction is equal to 0. So this is what I'm already going to start to do. Let me show you this. Oh, I got to get rid of that too. I do have a shear stress. I'm going to draw that. And I'm going to put this, I know I put it over on the side because in the middle here I'm going to put my diagram for my coordinate system. So this is sigma x is equal to 8,000 psi. Sigma y is equal to 0. I don't know shear xy. That's my unknown. My angle, well, we got to figure out our angle a sec. And then what they're telling me is, right? I've got to go back to the problem statement. The normal stress on plane AA is also equal to 8,000. It is unfortunate that they're both 8,000 because I think that makes this problem a little harder to understand. But sigma n is also 8,000. All right. What's my angle? Well, let's draw our coordinate system. I've got x. I've got y. And now my plane looked like, it looked like that. I'm gonna draw that while I got the picture up. Let's see, the rise is 3 and the run is 4, so it's just less than 45 degrees. That's 4 and that's 3, right? And so now I guess I gotta pull up a calculator and figure out what that angle is. That is going to be equal to theta. Theta is equal to arctangent of rise over run. So, okay, hold on a sec. I got 36.9. Theta is equal to 36.9. That's this angle here, 36.9. But that's not the normal. The normal is this. That's my normal. That's n. And so that's going to be, well, 90 minus 36.9. So that's going to be 53.1. Negative 53.1. Negative 53.1. And if I've got that, or sorry, I could have just taken the 36.9. I could have just added 90 to that and gotten 126.9 or really, something like 127 degrees. Skip the right little. It's close. It's good enough. And then I'm going to go through that, but now my equations, right? I'm going to write out that top one. Sigma n equals sigma x times cosine squared of theta plus sigma y sine squared of theta plus tau xy cosine. Oh, sorry, I dropped a 2 in there. Yeah, 2 times the shear stress sine theta cosine theta. If you look real carefully, I wrote my sine and cosine in the backwards direction after slipping in the 2. I know that's 0. And then I can start rewriting this. This is 8,000 equals 8,000 cosine squared of 127 degrees plus 2, and here's my unknown, tau xy cosine of 127 times sine of 127. And now rearrange and solve, but now those are all just numbers. Those are all just numbers. And I'm going to get the tau, that shear stress is equal to minus 5.33 KSI. So now I can go back and plug that in here. Minus 5.33. That's actually an answer. That's not a given, so that would get my box. The reason I want to put that up there is if we go back to our problem statement, find the magnitude and direction of the shear stress on the inclined plane. Now I want to go to this other equation. I want to go to my tau nt equation, and I want to know sigma x, sigma y shear, and the angle. And then I can do that. I got to wrap up because you can hear the dog howling downstairs. Anyway, that's our answer. If you would keep plugging away, sorry, I should have labeled that xy, and then if you keep going, you're going to get that tau nt is equal to a positive 5.33, and I just think that's kind of interesting. But Moore's circle would explain all that to you also. And that's almost what's next for our homework stuff. So, hope you're doing well. Be well. Take care.